Okay, so this is 7-1, the beta lesson. So it's going to pick up right in the textbook. Here's the question, example 4. So we're on page 382 of your book. If you want to bring up your copy of the book, or you can just look up here. What's the question asked? It gives a car moving with an initial velocity and an initial acceleration for 8 seconds. How fast is the car going when 8 seconds are up? How far did the car travel during those 8 seconds? So think about this. For this problem, we have to organize what we were given. So I built an H chart. My H chart is actually going to have another column. Because I would have time, I would have position, I would have velocity, and I would have acceleration. And at time 0, the velocity is 5. And they're asking about time 8. And they say, how fast is the car going when 8 seconds are up, and how far did it go? So this is what you need to do. You build the table, and you identify what's being asked. That's all. Because this takes that question, they just organized it for you. Because you were given initial velocity, and they want to know the velocity at that time, and they want to know how far the thing traveled. Logical? Do not just start typing stuff in your calculator. Organize the information. So we're here. Here's the table. So I said acceleration is the derivative velocity in the second derivative position. You don't have to write all that. But this top, or the second row, is what we have on the board. So if you're at home, I know you can't see what's written on the board, but it's the second row on the PDF. So we need everyone, whether they're in the building or they're at home, to just write that table for this problem for the second row. Because that's how you're going to do the problem we sent you to, with this being the example. Okay? So now what? Well, we're going to anti-differentiate acceleration in order to get velocity. So we were given 2.4t. So we do the power rule in reverse. And we get 2.4 t squared divided by 2, which is 1.2 t squared plus the constant. And we want to evaluate that from 0 to 8. Okay? So if we put 8 in there, we would get 64 times 1 2/10. 64 times 1 2/10 would give you 76 8/10. The area under the acceleration curve gives you the change in the velocity curve. And the change in the velocity curve was 76 8/10. And that has to be added to the initial velocity. And that's where the 81 8/10 comes from. Logical? We don't need to do the calculator. The 0, right, he's going to give you a 0. So we would just get 64 times 1 2/10. And that would be the area of the curve, like in essentially would be this. 1.2 times 8 squared plus 5. Subtract 1.2 times 0 squared plus the constant, which was a 5. And that 76 8/10 represents the anti-differentiation under the acceleration curve. So that's telling you, ready? The area under the curve is the change in the height of the parent grid. And the parent of acceleration is velocity. So we're here. The 76.8 represents what we're going to add to this initial value, and we're there. Good? Now what? We want to know the change in position. So we have to anti-differentiate velocity. So we would get 5t to the 0, anti-differentiates the 5t to the first divided by 1. 1 2/10 t squared, anti-differentiates 2. 1.2 t to the third divided by 3, which is 4/10 t to the third plus the constant. But the constant is going to subtract out every time. The constant will always subtract out if we have definite integration. Doesn't mean it's not there. And if it helps you to put the constant there all the time, because it's a prompt to put it there, if it's indefinite, that's fine. Because better you write too many constants than not enough. Because if you omit the constant in indefinite integration, you will be penalized. Why? Because the area under the velocity curve, I'm sorry, the area under the acceleration curve is 76 8/10. Yes? That means that's the change in acceleration 0 to 8. The change was 76.8. They told us the initial velocity was 5. So that was, in a sense, the initial height. So you add the initial height to the change, you get where you are at time 8. Everyone on board with that? So now what? This would give us, ready? 5t plus 4/10 t cubed. Because the 0 is going to give us a 0. That gives us to 244.8. Okay? Except after 8 seconds, you didn't travel 244 miles in 8/10. That doesn't make sense. And if this were multiple choice, that would be choice A. Why is it fouled up? The units don't match. Because this is miles per hour, and we did 8 seconds. So we have to do a size change to that, or a scale change. So we go here. Dimensional analysis. This is our answer. 244.8, which is miles per hour. Miles per hour. times 8 seconds times 1 hour is 3,600 seconds. So this is ready? This thing right here is 1. 1 hour equals 3,600 seconds. And that gives you this many miles, which is that. Now, 4 years ago, we got to this problem, Mark Olivetti, as in 5 in BC. Didn't take statistics, I'm not happy about that. But Mark Olivetti said, well, I'd rather do it this way. Instead of doing that at the end, I'm going to do the size change first. And I'm going to make my initial velocity 5 divided by 3,600. Instead of making my initial velocity in miles per hour, I'm going to make it in miles per second. This would take you right to the answer. And there's the graph. So that's up to you. If you want to do it the way Mark did it, that's why it's up there. Because somebody sitting here had a suggestion to complement what's there. We're not just saying, oh, repeat what's in the book. Rather, let's repeat. We're saying, be open-minded, just be creative. And Olivetti was creative. Okay? So, this is up here. I mean, you can scroll yourself if you want to see Olivetti's explanation. And you're just going to go to problem number 9. All right, so we're going to pause the video. Problem number 9. Now, in this case, the initial velocity was 0. You got to be careful. So there was nothing to add to the area of the curve. And here's the power rule in reverse. And that would give you from 0 to 9. And again, the 0 is giving you a 0, but don't be presumptuous about that. That gives you 63. That is the velocity at 9 seconds. Then what? Power rule in reverse. We would get the area under there is 234 9/10. But that's how far it would have traveled in 9 hours. So here's the dimensional analysis, which takes us to 0.065, ready? 3 decimal places. You truncate something to 3 decimal places on May 4th, and you're going to get full credit. Right, so it's the same problem with different numbers. But the difference also being that 0 was in the initial value for velocity. Okay? So 7-1 beta. Because we went over the problem at the beginning. We went over this question, I think, last week, with just a calculator question, where we anti-differentiate that. Just type f of t in y1, and you math 9 it from 0 to 60. Okay? So if you're at home, you are